want to study electric field on a system of opposite charges. So if two equal and opposite charges are separated by a small distance, this system is said to form a dipole, as you can see in the figure, where the charges q and minus q are separated by distance 2l. The product of magnitude of charge and the separation between the charges is called the dipole moment, and the SI unit is coulomb meter. Mathematically, we can write it as P is equal to Q into 2L. Note that dipole moment is a vector quantity. Equation gives its magnitude while the direction is from the negative charge to positive charge along the line joining the two charges. Defined a dipole and a dipole moment, we are now in a position to calculate the electric field due to a dipole. Let's first calculate the electric field due to a dipole at an axial point, that is end-on position. Consider the figure. This be a negative charge Q and this point charge be a positive charge Q. Let this be A, this point be B, the middle point be O. Will be, and the distance AB will be 2L. We'll be calculating the electric point at an axial point P that lies on the axis of the dipole. Let this distance be R. Now, the electric field E1 due to the point charge plus Q at B is given by E1. The direction will be in this direction. We'll find E1. E1 is equal to K Q by, what is this distance? This distance is R minus L. R minus L square. Due to this negative charge, E2 will be in this direction. So E2 is KQ by, what is this distance? R plus L. So R plus L square. No. The resultant of these two vectors, so the resultant field E at P will be in the direction E1 because R minus L is less than R plus 1. So E1 is greater than E2. So resultant field E is equal to E1 minus E2. No. R plus L square is R square plus L square plus 2RL, and this will be R square plus L square minus 2RL. And this will be R minus L A minus B into A plus B will be A square minus B square. This gets cancelled, this gets cancelled. So what are we left with? Let's do some simplification. with this thing. K can be written as, now let's write this 2L together and 2R separately. Q, 2L, 2R. What is this? This is the dipole moment. And here R square, power square, so we'll take R square separately. So this can be written as 2, this R will go, this one will go 3. So this R will go, this one R will go. So what will come? This is dipole moment P. So 2P by 4 pi epsilon naught R cube 1 minus L square by R square. Now R is very much greater than the L. So L square by R square is comparatively small and we can be neglected. Therefore, we get E is equal to 2P by 4 pi epsilon naught R cube. This is the dipole moment at the point P. Now let's calculate the electric field due to a dipole at a point on the perpendicular bisector. Broad on position. Here we'll calculate the field at point P, which lies on the perpendicular bisector of the line joining the charges. So this is for negative charge Q, this is positive charge Q, distance between them is 2L. So we are done. This is the dipole. Let this point be O, let this point be A, let this point be B. We are going to calculate the electric field E due to the dipole at a point P on the perpendicular bisector. So this will be the point P in the perpendicular bisector. Let OPB R and OAB, this is L, this is L. Okay. This be the angle theta. The field T due to charge Q, positive charge Q at B, will be in the direction, this direction, E1. So E1 will be K Q. Okay, let's change the color. Now the electric field due to the positive charge Q B at B will be in this direction. Let this be E1. E1 is equal to K Q by, this is the distance now. So Pythagoras theorem, R square plus L square. And the electric field similarly due to the point charge, negative charge at A will be towards it. This will be E2. So E2 will be KQ by R square plus L square. The resultant will be in this direction. So this is angle theta, this will also be theta. Let us do this resolution part here. So this is E1, this is E2. We saw the angle this. So this is theta. Let us resolve this vector even. Let's note here this is also theta. So the components parallel to AB are E1 cos theta and E2 cos theta. So this is E1 cos theta. They are in same direction. The components normal to AB are E1 sin theta and E2 sin theta. They are in opposite direction. They cancel each other. Hence, the magnitude E will be, the resultant electric field's magnitude E will be E1 E will be E1 cos theta plus E2 cos theta. So let's do this now. So the resultant field will be E1 cos theta E2 cos theta. What is E1? K cube by R square L square. And E2 is also K cube. So I missed cos theta. Okay. Now what is cos theta? Cos theta is, let me write it here. This is L now. L by root of K L square plus R square. Let's replace. These are same component. So 2, how can we write it? 2K cube by, let's simplify. What is K? K is 1 by epsilon naught. If I take R square out, it becomes R cube. 2QL is P. And here similarly, same as we done before, since R square is far greater than L square, we can neglect this component L square by R square. So simplifying this, we get 1 by 4 by epsilon naught. This is dipole moment P by R cube. We note that the electric field due to a dipole at a point in rod-on position is also inversely proportional to the third power of the perpendicular distance between P and the line joining the charges. I have summarized the two cases we discussed in this slide. Note that if we compare the electric field in both the cases, it is proportional to 1 by R cube. But there are differences in details. The magnitude of electric field in end-on position is twice the field in the broad-on position. And the direction of field in end-on position is along the direction of dipole moment, whereas in the broad-on position they are oppositely directed. Electric dipole in a uniform field. Let's examine the behavior of an electric dipole when it is placed in a uniform electric field. Now, what is a uniform electric field? It is a A uniform electric field has constant magnitude and fixed direction. Such a field is produced between the plates of a charged parallel plate capacitor. We'll be discussing about capacitor in further chapters. Let the x-axis be the direction of electric field points along it. Suppose there is a dipole that makes an angle theta with the field direction. Let this be the negative charge, this be the positive charge, this distance be 2L. Now, a force QE acts on the positive charge along the x-axis, positive x-axis. So this is the direction of electric field EQ. An equal force acts on the negative charge in the negative direction. So this is QE. Two equal, unlike and parallel forces form a couple and tend to rotate the dipole in clockwise direction. This couple tends to align the dipole in the direction of external electric field E. So now we'll calculate the torque tau that is given by force into arm of the couple. Now what is the force? Force is QE and arm of the couple is Y. Y can be written as so this is 12 Y. So this is also if you take this to be a triangle, this is theta. This is 2L, this is Y. Y can be written as 2L sin theta. So QE 2L sin theta. What is 2QL? Dipole moment P. E sin theta. This is cross product. P cross E. Note that when theta is 0, the torque is 0. And when theta is 90 degrees, the torque on the dipole is maximum, equal to P. So we can conclude the electric field tends to rotate the dipole and align it along its own direction. This is the behavior of electric field in uniform. This is the behavior of an electric dipole in a uniform electric field.